this is Dr. Johnson, and this is Physics 103. We're going to be building off of what you guys did last week with Professor Ashcraft, where you were doing a little bit of graphical analysis. You're going to be looking at graphs today. You're going to be making graphs today. It's going to be awesome. So we're going to be using this cool device. It's a Pasco motion detector, and we're going to be detecting some motion. It's kind of neat how this thing works. It uses echolocation, kind of like bats and dolphins do. So that's kind of neat. So first, before we get into that, I want to talk a little bit about graphing. I know Professor Ashcraft took you through some of the basics. I want to take sort of a review, because it was a week ago. It was a long time. It's hard to remember all that stuff. And maybe a couple new things, some stuff from my perspective, which might be helpful. So I know you talked about a graph of position versus time. So over here in the position graph, we have meters. Over here on this axis, we have time in seconds. And we can tell there's a lot of information you can get from this graph. First of all, you can tell where something's at any given time. Let's say the graph, I don't know, looks something like this. If I want to know where am I at this time, whatever time that might be, I want to know where I'm at. Well, I just go up to the graph, right at that spot, go over to the position axis, and whatever that reads, that's going to be my position at that time, which is pretty cool, right? Like, I can look at this picture and know something about the real world. That's why we love graphs in physics, because we can graphically represent a lot of information, both mathematical information and just physical information of where you're at in space, which is pretty neat. But that's not all. It's sort of a 2-for-1 deal here, because as you did last week, if you can figure out the slope of this graph, how steep it is, you can tell how fast you're going, which is pretty cool. From the slope of a position time graph, you could find the velocity or the speed. You can find out how fast it's going. Pretty cool, right? 2-for-1. So the slope, if you remember from your probably middle school math class, or even maybe before that, is the rise over the run. It's how far up you go divided by how far over you go. So what does that mean exactly? How far up you go is a change in your position, because that's position is the up and down. How far over you go is a change in time, because this is the time on that graph. So change in time, change in position. You've probably seen that before. If you've taken our lecture, you've probably seen it in the lecture. Change in position divided by change in time. Oh, it's your speed, right? It's how fast you're going. So the slope of that line gives you the speed. Pretty neat. You can get the position, you can get the speed. Awesome. That's not the only kind of graph we use in physics, though. We also use a velocity versus time, or a speed versus time graph. Those are different, and you're going to learn about how they're different when we talk about vectors. For the time being, as long as you're going in a straight line, the numbers are going to be the same. We can have our velocity on our y-axis and time on our x-axis. So change in position, which we said was how fast you're going, that's measured in meters. And change in time, here at the bottom, is measured in seconds. Well, that's meters per second. And that's the unit we're going to use for that particular physical quantity. So this is going to be in meters per second on this axis, and this is in seconds over here. And this is a cool graph, because it also gives us information. It'll tell us how fast you're going at any given time. Let's say 3 seconds go by, and I want to know how fast I'm going. I go 1, 2, 3. I look for the 3-second mark, and I go up to wherever my graph is. It's going to tell me how fast I'm going. So let's say the graph looks something like this. Now, with a little bit of experience, you'll be able to look at that and say, oh, I know exactly what's going on. I'm going at time equals 0, I'm going whatever speed this is. Let's say it's 3. So at time equals 0, I'm going 3 meters per second. At time equals 1, I'm going 3 meters per second. At time equals 2, I'm going 3 meters per second. So for that particular graph, I'm going the same speed the whole time. It's a flat line, but I'm still moving the whole time. I'm just moving at the same speed. 3, 3, 3, 3. So my example before, go to 3 seconds, go up to here, I'm going 3 meters per second. Awesome. Now, with the position graph here, we could get two things for our, more bang for our buck, right? 2 birds, 1 stone. 2 quantities we can figure out from one graph. I can figure out where I'm at, I can figure out how fast I'm going. Now this one, I know I can figure out how fast I'm going. Awesome. What else can I figure out? Well, before we looked at the slope, this one doesn't have a slope, but what would the slope tell us? What if we did have a slope? Well, let's do one. Let's make it so we have a slope. I can do that because I'm the teacher. Now we've got a slope. Now it's a sloping line. I start at 0 meters per second, but after 1 second, now I'm going some speed. I'm speeding up. At 2 seconds, I'm going faster. At 3 seconds, I'm going faster. Every second, I'm going to go up on the speed line. So I'm increasing my speed. If I take the slope, the rise divided by the run, that gives me a change in velocity divided by a change in time. What's that? Change in velocity divided by change in time. Well, you probably learned about that in your lecture. You probably learned that that is equal to the acceleration. So the slope of a velocity time graph, it's going to give you the acceleration. So I can get, from this graph, I can get the velocity. I can just read the velocity. I can also get the acceleration. There's one other bonus thing you can get. Now, I'm going to take a quick time out here. For those of you who might have taken a calculus class in your life, there's another word for slope. It's called the derivative of a function, or the derivative of an equation. So these things, the change in and the change in, if you're a calculus type person, you know that that's a derivative. You can find the derivative, and that's something I'm going to probably talk to you about if you're in my class at some point, just to show you, because it's good to know stuff. Do we require you to know calculus in this class? No, but it's kind of fun to know things. So there's one other thing we can get from this. One other quantity that we can measure. If I measure the area underneath this curve, again, if you're a calculus type, you know that's called an integral. But again, you don't have to know that. It's just fun to know things. But if I measure the area underneath that graph, I can figure out how far I've gone during that time. If I measure the area from 0 seconds to 3 seconds underneath the line made by my graph, it'll tell me how far I've gone. So it'll tell me my displacement during that time period. That's awesome. You can get so much information from these graphs. From the position time graph, we can find the position, we can find the speed. From the velocity time graph, we can find the velocity, we can find the acceleration, and we can find out how far we've gone, the displacement. We can find out how far, how fast, and how fast my speed is changing. Lots and lots and lots of information, which is why we love graphs in our physics classes. Now, all of this has been pretty fun for me, but I think it's time for us to have fun together. I think it's time for you guys to get involved. So what we're going to do in the lab today is we're going to look at some graphs. If you turn to the Graphing Motion Match the Graph lab in your lab manual, you're going to see some pictures of some graphs. And there's going to be some questions about them. What you're going to be doing during this lab is looking at those graphs and trying to determine what those graphs are telling you about the motion of the thing that's getting graphed. So something is moving, and we're making a graph about the motion of that motion, the motion of that thing that's moving. And you're going to be interpreting that graph. You're going to figure out what, in the real world, that graph is representing. What does it look like in real life? So there's some questions about them, which you're going to answer. We'll go through that in a second. And then, on the next page, there are some graphs for you to try to match. Now, if you were here in this room with us, you'd be hooking up one of these things, and you would be matching that graph. You're not here, unfortunately. That stinks, because it's really fun to try to do this. You get to do all kinds of crazy stuff to try to figure it out. Well, we're going to give you the chance to try to figure it out anyway, and then we're going to show you. We're going to represent at least a few of these for you. So I hope you're ready, because that's where we're going next. All right, so if you look in your lab manual, in the upper left-hand corner of the page with all the graphs on it, you'll see a graph that looks kind of like this. We have position on the y-axis, time on the x-axis, and the graph itself, the line comes out flat, which you should know what that means, because I just talked about that, I think. And then it comes down, goes back up, sort of like a V, and then it flattens out again.
Well, you talk about a velocity graph being flat.
Oh, so I
This
guess
is a position graph being flat.
you're gonna have to make a little bit of an inference here. So next to the graph on the page, in the lab manual, you're going to see a box that says describe the motion. Now, you would be doing a little bit of trial and error with the motion detector and figuring out how to make this graph out of your own personal motion, moving in front of the motion detector. We can't really do that when you're not here. So what I'd like you to do is write down what you think is happening. So there are essentially 4 pieces to this graph. There's a piece right here where it's flat. There's a piece right here where it's angled downward, sloping downward. There's a piece right here where it's sloping back up. And then there's a piece here where it's flat. Those 4 different steps are all parts of this motion in this graph. So I'd like you to write down what you think is happening in this motion, all 4 parts. We'll give you a little bit of time, and then my lab partner, Professor Ashcraft, and myself, we're gonna do it. We're gonna actually make this graph. You'll be able to see it. So take a second, see if you can figure out what's going on. What's happening in a position time graph on a flat, horizontal, straight line? Well, at this time, it's at some position. At this time, it's at some position. At this time, it's at some position. Oh, those positions all have the same value. That's a hint. I know I said I'd let you do it, but it's the first one. I'll help you out a little bit. This one, the position starts off here, which is a big number for position, which means it's kind of far away from the sensor. But as time goes on, the position value gets smaller, which means the number for the position, the value of the position is getting smaller, which means the distance is getting smaller between you and the sensor. Huh, okay. So at this point, I think you should have had a chance to write down what you think is gonna happen. If not, you could pause, write it down, and then hit play. And all right, I'm just gonna continue what I was talking about. So here, it's a flat horizontal line. At every single time down here on this x-axis, the position value stays the same. So it's some distance away, and relatively far away because it's near the top of the graph. As this goes down, I'm moving. But what direction am I moving? Well, I start off kind of far away and I end up kind of close. So I'm moving towards the sensor. We're going to talk about having positive and negative velocities. In this case, it's a negative slope, which means I'm moving in the negative direction. In this case, it's sloping upwards. It's a positive slope, which means I'm moving in the positive direction. Professor Ashcraft, he always tells you, always determine what the positive and negative direction is. It's really, really important. So in our case, the negative direction is towards the sensor. We're decreasing our distance. The positive direction is away from the sensor, where we're increasing our distance. And then we get up here and it's flattening out again, which means our position isn't going to change anymore. So I'm going to start at some position, and if I go across, hey, that's the same position. It's the same number. I'm going to end up at the same place that I started. So let's give it a try.
So can you describe that sensor? I mean, isn't the
man.
sensor a whole lot like an eyeball?
It kind of is. Now, when he hits the play button, you're going to hear some clicks. Those clicks, it's sending out a signal. The signal is hitting, in this case, it's going to be hitting my board, and it's going to be bouncing back. And the computer's smart enough to do a couple calculations to figure out how long it takes, and it knows the speed that that signal is going out at. So it can figure out how far away you are, and it can figure out how fast you're moving either towards or away. So it's seeing a reflected signal. Is that what you're getting at, or do you have more to
I
add?
am. I'm just saying that the farther away that you get out, it's more and more of a positive number. So that when you go farther away, you're going to get a big number, and as you get closer to it, you're going to get a small number. And also, the sensor can't see anything behind itself, just like I can't see behind me, even though I am a teacher. I don't have eyeballs in the back of my head.
That's true. It's one-dimensional, one-directional. So if I go this way, great, it can still see me. You can see this, I don't know if you can see it in the video, but there's a little gold reflective surface. That's where it, quote-unquote, looks out of. But now, with other classes, I've seen students who are doing this trial and error and trying to make the graph do certain things, and they're like moving their panel up and down or side to side. Well, it just doesn't work. It's sending out a signal in one direction and collecting signals from one direction. So let's give it a try.
Okay, I'm going to press the record, and I'll keep recording. You tell me to stop.
All right, so I get my nice flat line, I move forward, I move away, and then I get my nice flat line.
Hey, that looks great. I got myself a flat line right here. I've got a pretty gosh darn good straight line. downward, which means you're going closer. I've got a pretty gosh darn straight line going upward, which means you're going farther away, and then we're back to the straight line again.
I
Excellent.
didn't quite get the point down here at the bottom.
It's awfully hard to get these inflection points.
Yep.
This one and that one, yeah, it's very hard.
This is an idealized graph. That one's a real life graph. So, yeah, I think I'll accept that.
I'll accept that too.
I give myself credit. Now, this one has a lot of straight lines on it. Straight lines for me are kind of easy to interpret. The next one, not so much. We'll get to that in just a second. All right, the next graph down the list looks kind of like this. Now, this is just a rough sketch, but it's pretty close. We're starting off down here, and we're going up like this. But unlike the last graph, this is not a straight line. I don't know that we've talked about curved lines yet. We've only talked about straight lines. But I want to give you a second to just think about it. I want you to write down your hypothesis. I want you to write down what you think this is describing. So take a second and do that. Okay, if you still need more time to write, pause the video, start it up when you're done. So we have talked about the slope of a line. And you might say, well, it's a curved line, so it doesn't really have a slope per se. But that's not really true. If I look at any one point on this graph, it's sloping a little bit. And if I zoom in more and more, now those of you who've taken calculus sometime in your life, you're like, I know what he's talking about. But if you've never taken calculus before, you can still know what I'm talking about because it still makes sense just thinking about it algebraically. If I take a little tiny chunk of this, it looks like a straight line. And that straight line is going to be sloping a certain amount. Now down here at the bottom, every one of these little chunks has kind of a small slope. It's only angled a little bit. But as I move farther and farther and farther up the graph, see how the angle of this ruler is changing? Down here it's kind of flat. Up here it's kind of getting slopey. Up here it's getting really slopey. It's getting more and more and more steep as the graph moves forward in time. Whoa, let there be light. And there was light. So what's going on? We talked about what the slope of a position time graph is. We said it's velocity. So here, the slope is kind of small. It's kind of flat, so that means it's not a very big slope. Up here, the slope is kind of moderately big. Now, the slope is the velocity, and the slope is getting bigger and bigger and bigger. The velocity is getting bigger and bigger and bigger. So what's going on? It's speeding up. It starts off close, because it's got a small position number, and it ends up far away. And in the process, it's speeding up.
Is it speeding up positively or is it speed up
Oh,
negatively?
that's a really good question. So is this a positive or negative slope? Well, it's sloping up, so it's a positive slope, but it's a small positive slope. Moderately large positive slope, and bigger and bigger and bigger. The slope is getting bigger and it's getting more positive. It's getting steeper and steeper and steeper in the positive direction. So I'm speeding up and I'm speeding up in the positive direction. In the last graph, we said the positive direction was away from the sensor. So I'm speeding up and I'm speeding up away from the sensor. So let's give it a try.
I like that one better.
That was way better.
And again, don't look at this last part or else you're going to see Dr. Johnson falling into the lab table. But if you look at this part right here, he stopped, he's going slowly, and then right up here, if he took the tangent up to there to about there, you can see he's going faster and faster and faster in the positive velocity. Excellent.
So far, so good. Onward. All right, so the next graph, we start off close to the sensor, and we start moving. It's got a positive slope, so it's moving away from the sensor. It's a little bit curved, so I'm going to speed up as I go up. I get to a point up here at the top where I stop, and I change directions. This is what happened with our V shape. Remember that how I kind of had a little curve? It's because I was changing direction. It's changing direction kind of gradually, and then something happens. Now, I don't know. I'm not sure. I want to give you a chance to kind of think about this and write down what you think is going on for this graph. So if you need time, pause, write down in the box what you think is going on. Okay, since I gave you a chance to pause, I'm just going to keep going. Some sort of gap here. I don't really know what to do. I guess I could jump out of the way of the sensor maybe, or, yeah, I guess I'll try that and we'll see what happens. But as I'm moving back towards the sensor, I guess I'll jump out of the way for just an instant and jump back in and come back, and we'll see what happens on the graph.
Yeah, I found that if I turn the camera off or turn the sensor off and turn it back on, I get a whole new graph, so that doesn't work for me.
Yeah, so that's probably not it, but we'll give it a go. We'll see what happens. Well, that didn't work. You can see in the data, I got that spike. Professor Ashcraft's going to point to it.
Yeah, right up here. Looks like, well, what's going on here at 2 meters? Well, you hit the other lab table.
Yeah. So remember what the sensor's doing, right? It's sending a signal out and it's bouncing back. So when I get out of the way, the nearest thing that it can see, quote unquote, the nearest thing bouncing the signal back is that next lab table, which is about, what, 2.5 meters-ish away. So yeah, I can't really do that. So I guess the moral of the story is, see that chunk that's missing there? You can't do it.
No.
It can't be done. So sometimes I've had students say that there was a sensor malfunction there, and yeah, maybe, okay, I'll buy that. But I would also buy that this one is impossible. Now, if you described accurately how to get this part that you can see, except for that gap, good job. We'll take that too. All right,
Yeah, I got one thing to ask you, Dr. Johnson. You switched directions here, right?
I did.
I mean, you're going out, and then you're going in. Well, what is the slope at the very tippy top here?
Yeah. I'm gonna ask you a question.
Okay.
When I take this marker and I throw it up in the air,
Yeah.
it's going up, right?
Right.
Well, until it's coming down, right?
Yeah.
So what happens at the very top, right at the apex of the throw,
well,
right at the peak?
there's an instant where it's gotta like just be neither positive nor negative. It's
Yeah.
gotta be zero.
It was going up. Now it's coming down. Somewhere in the middle, it had to go through zero, right?
So it stopped.
Yeah. So same thing is true for my motion. I was going back, and then I was going forward. At some point, I had to be stopped in order to be going from that direction to this direction. So at that point, at that peak, at the apex of the throw or at the transition of my motion, I'm actually not moving at all, just for
Wow.
that instant.
Cool.
All right, we got a fun one now. This is probably my favorite of the position time graph column. We got 2 hills here. So pause the video, write down what you think is going to happen. All right, great. So now we're going to talk about what's going to happen. We kind of saw a bump like this on the last graph, the one that had the little hole in it. Well, I'm starting close and I'm moving farther away, and then I'm going to start moving close again, then I'm going to move far away, and then I'm going to move close again. So I'm going to be moving forward and backwards and forwards and backwards. Or I guess actually moving away from the sensor, then moving towards the sensor, moving away from the sensor, moving towards the sensor. Sometimes I ask my students to figure out an instance of real life motion where this might be the case. And I had hockey players in my class maybe 2 semesters ago. And we said, if you have the sensor next to them, maybe it's the skating motion where they're going away, towards, away. So that's one example. Can you think of an example? Jot it down. I'd like to see yours. Maybe I'll steal it and use it in class. All right, let's give this a go. See if we can make this work.
All right.
That's not bad. I can do better.
Yeah, you probably can do better. Now, you might be wondering, I mean, yours seems more spaced out than theirs. But what I can do on my Logger Pro here,
Look at that.
I think that looks a little better.
That's not bad.
Not bad at all.
Oh, I'm not even on the screen. So, there you go.
I'll take it.
All right. That's good enough for me. All right. So now we got this monster.
Well, it's the same graph, you just
Yeah.
tipped it over.
Exact same graph, right? Just turn it 90 degrees. What do you think's going to happen here? Pause the video. Write it down in the box. All right. Well, I got to admit, I'm kind of stumped on this one. Professor Ashcraft, you have any ideas?
Well, it looks like, you're, for 2 seconds, you're like 2 different places. For 3 seconds, you're like 1, 2, 3, 4 different places.
Yeah, I'm moving back and forth, but I'm moving back and forth on my x-axis. And what's on the x-axis? It's time. I don't know if you can still read that or not, but it's time. So I'm moving forwards and backwards in time. I mean, I can move forward and backward in space. That is something I do all the time. But moving forwards and backwards in time, that's not really something that I know how to do, at least not yet.
Isn't there what's that function rule? Do you remember that?
Yeah, there's
algebra?
the line rule of functions,
The line rule,
right?
yes.
So this, my friends, is not a function. So we can't do this. This one it's out. So if that's what you said, good for you. If you said something else and it works, then awesome. You got to teach me how to time travel because I'm excited to learn. All right, so that's the last of our position time graphs. We're going on to the next level, right? This is where it gets real, velocity time graphs. All right, so we are on to velocity versus time graphs. Check that out, velocity versus time graphs. All right, so we did talk about them a little bit at the beginning. There's a ton of information you get from velocity time graphs. Right now, the only thing I'm concerned with though is the velocity. How am I moving? Now, with the position time graphs, because of the nature of the sensor, every single measurement was above this line, above that axis. Everything was positive. Well, that's not the case with this one, right? We're starting off down here below that line. So take a second, pause the video, write down in the box what you think is going to happen. The good news is you can't really be wrong, right? You're making a prediction. I mean, you can end up not correct, but we're not judging you on that. We're hoping that you think about it and see if you're right. That's half the fun. So take a second, do that. All right, let's talk about it. So what does it mean if the graph is down here? I don't know if you can tell, it's a green line. Kind of looks black on the screen, but it's a green line right here. This green line here at the bottom is below the axis, which means it's in the negative zone. It's less than 0. So it's got a negative velocity. What does that mean? Well, we said the negative direction was towards the sensor, so it means that my velocity, it's a flat line, so it's not changing, but it's towards the sensor. It's in the negative direction. Then suddenly, boom, it's up here. It's in the positive area. It's above that line. It's going to be a positive number, which means it's going to be away from the sensor in the positive direction. So I'm going to start moving towards it at a constant velocity, and then suddenly, boom, I'm going to start moving away from it. Let's see if we can pull that off.
Oh, hang on, I've got to make my graph different. I've got a position versus time graph. I'm going to make it into a velocity versus time graph.
Hopefully you saw where he clicked on that. He just clicked on the word velocity. And that's how you decide what to put on that axis.
Okay?
Okay.
Well, not one of your best ones, but if I take a look at right here to right there, I'm going to declare that good.
All right, so yeah, the second right there is where I bumped into the desk. The first right there is I should have already been moving. So notice that it doesn't start at 0. My velocity doesn't start at 0, and I stopped. So, well, that was a mistake. But once I got up to speed, it was a pretty flat line. Now, you could critique the fact that this vertical line on my graph isn't quite vertical. But what would a vertical graph here be? It would have a slope that is, well, you can't really calculate that, right? It's rise, which you could figure out, but it has no run. It has no x change in the x-axis. You can't divide by 0. That's not even possible. So, while you could critique that, I don't think you could reasonably hold me accountable for it because it's not even possible. We can get it as steep as we can, which I did, but it can't ever be completely vertical like that.
Well, you know what that graph, your theoretical graph, reminds me of? I used to play racquetball in my younger days, and I could hit a racquetball pretty gosh darn fast. And it would come in at the wall at a certain speed, and it would bounce off the wall at almost the same speed. And when it came in, it was like pretty constant speed. And when it came off, it was like pretty constant speed too. And it spent hardly any time on the wall whatsoever. Now, I don't expect you to be a racquetball, sir.
Oh, no, but I do enjoy racquetball, so
Yes.
I love that example.
How fast do racquetballs get hit? 60?
That's a good question. I'm not 100. I used to know that, but I don't know anymore.
Okay, so let's say that it comes in at 60 miles an hour and leaves at 55 miles an hour. That's a pretty gosh darn good acceleration.
All right, so our next velocity graph. We have a straight line, but it's not a horizontal straight line. It's angled. So what does this mean? What kind of motion would make this? Pause the video, write it in the box. Okay, so what do we have?
Now, when we had a position versus time graph, a straight line meant something special. Yeah, when we had a straight line and we had a linear slope on a position versus time graph, that was something special.
That's true. So the slope on a position time graph was equal to the velocity.
Right.
And if it's a straight line, the
Mhm.
slope isn't changing at any point.
Then the velocity wasn't changing.
So the velocity wouldn't be changing. But for a velocity time graph, the slope means something different.
It's the acceleration.
Yeah, so what does that mean? Well, that means the acceleration at all points on this graph is going to be exactly the same. The acceleration isn't changing.
Okay, and we can also tell right now if it's positive or negative or zero, because that's a positive slope.
Correct. So it's accelerating in the positive direction, which means it's accelerating away from the sensor. Got to be clear with our terminology. We have to be very consistent. Once we've decided what's positive and negative, we have to be consistent throughout the problem. Now, the velocity in this part is below the line. Even though it's sloping up and has a positive acceleration, the velocity is in the negative direction. So initially we're moving towards the sensor, but the velocity starts off big down here and gets smaller and smaller and smaller until it gets to that spot right there. When it crosses this line, the velocity is 0.
So when the velocity is zero, we talked about that other curve, you're standing still.
Yeah, but only for an instant, because at the very next moment, as we continue in time, I start moving in the positive direction. So remember when we tossed the marker up and then it came back down? There's that instant where it's not moving. That's right here. That's what that looks like. So let's see if we can pull this off.
So if you're going positive velocity, then you're going away from it.
Correct. 3, 2, 1.
Oh my God!
I should do this for a living.
That was that. Oh. All right, we're going to neglect this stuff here, and we're going to neglect that stuff up there. But that is one of the best straight lines I have ever seen. Yep. Cool.
I should do this for a living.
Yes. Now, when I'm in my class, I tell people that if you can imagine that there's a sensor on the ceiling, okay? So that if it goes this way, it's negative. If it goes that way, it's positive. If I throw my keys up, whoops, and if they don't touch the ceiling. If I throw my keys up, and they come down to the floor. That's exactly what the graph looks like. Because if you look on there, there's a shorter amount of time where it's negative, and there's a longer amount of time when it's positive. And it goes up, and it comes back down to the floor. I am so impressed. You must be an athlete, sir.
All right, next down the list. We're getting close to the end. We're doing good. We're doing good work. So this one's really interesting. We have straight lines, but we don't have one single straight line. Remember before we had one straight line. Also, interestingly, you'll notice here's my axis. There's no graph anywhere up here. So take a second, write down what you think is happening. All right, so here's what I think is happening. Notice that I'm starting here. I'm starting at 0. I'm starting stationary. And then I start moving. Now, do I know where I start stationary? I don't. There's nothing about this graph that tells me where I'm at. I can figure out how fast I'm going. I can figure out the acceleration. I can also figure out how far I've gone if I really want to put my mind to it. If I had numbers on here and I calculated this area, I can figure out the displacement. But does it ever tell me the position? Professor Ashcraft, do you know a way to find the position from this graph?
Not the starting position, no. The only thing I can tell is how far it's gone from the area.
Yeah,
But
so
not the starting.
I don't know where it starts, but I bet we can figure out a good place to start. It actually doesn't matter where you start. You can start a mile away, you can start really close. As long as my velocity is always in the negative direction, it's still gonna give me the same graph. That's kind of cool. So I start off at 0, and then I speed up in the negative direction until I get to this spot right here. That spot right there, I slow down in the negative direction. I'm still moving in the negative direction because my velocity is always below that line. It's strange because the slope is different, but what does the slope tell us? The slope tells us the acceleration. In this case, I'm accelerating with a negative slope, so I have a negative acceleration. I'm accelerating in the negative direction. In this case, I'm accelerating in the positive direction. That might be a little bit confusing. We'll probably talk about it a lot in lecture, but you can be moving in the negative direction, but accelerating in the positive direction.
Yeah, people call that decelerating. I hate that word.
So, let's see if we can make it.
Oh, and then the last part, your velocity 0.
Yeah, see that little flat line there? I forgot to mention.
Yeah,
Velocity is not changing and it's staying at 0.
so you're staying still. Good. Good?
You happy with that?
Sure.
All right, I'm happy with that.
All right. Hey, if we look at this, he's still. He goes towards the sensor, goes from the sensor, and then he stops all the way there. Cool. All right. What I want you to do is I want you to imagine a long driveway, okay? Now, when I drive my car, I always put the car into the garage, which means I have to back out of the garage to the street. So I got this long driveway. All right, so I'm in the garage. And then I back it up, and then I slow it down when I get to the street. And then I stay here on the street, and I wait for traffic. That's it. That's what he did. He's in the garage, he speeds up, he slows down, he's still always going backwards. And he just stays. That's what he needs to. Good job.
We're in our last graph, the last one. Maybe the most complicated. Tell me what you think's going on here. All right, let's talk about it. So, we have our velocity. It's in the positive direction. Well, how do I know? Well, it's above this line. This line is my 0. Anything above it's positive. And it's big because it's way up here. So I have a large positive velocity, which means we're moving pretty fast in the positive direction. But it gets down here to the 0 pretty quickly. I know it's accelerating fast because it's got a big slope. The slope up here is steep. It's steep and pointed down, which means it's steep and in the negative direction. So I have a negative acceleration, but a positive velocity, which means I'm going to be slowing down till I get down here to the 0. And then I have a negative velocity. And the negative velocity is increasing, which means I'm going faster in the negative direction, but it's increasing less and less and less and less. It's flattening out. The slope is getting smaller and smaller and smaller. Now you might need to listen to that again, because that's pretty complicated. It's difficult to think about that, because so thinking about position, that's thinking about sort of one thing. Thinking about velocity is trying to think about 2 things at once. Thinking about acceleration, that's like thinking about 3 things at once, and that's pretty difficult. So if you need to listen to it again, no problem. That's why it's on video. But let's see if we can do it. Let's give it a try.
What I had some students do is they've actually broken this down. And they said, okay, like at 1 second, I'm going around +3. So I'm going like 3 meters a second all the way out. Oh, hey there, okay. And then like at 2 seconds, I've already stopped. I'm starting to go back in towards it. And at 3 seconds, well, I'm going about 1 meter a second in towards it. And at 4 seconds, I'm about 2 meters a second in towards it, twice as fast. And at 5 seconds, I'm about 2.5 meters. So I go out like a shot for a second, and then I slow down, and then I go back in slowly. Speed up a little bit, but still real slowly. Much slower than what I went out as. So we'll try that. Yes. All right. I'm going to take that. And I'm going to bunch it up just a little bit. Come on. Does that look pretty enough for you?
Yeah.
All right. Hey, we got it right here. We had a really good high positive velocity, and then it went down like a shot. And then kind of went slow. I want you to stop watching right about here. And that's it. Except for this little spike here, you nailed it, sir. You did exactly. So you went back fast, about a second, and then you slowly came back. All right.
Okay. So you guys have a little bit more work to do. You'll notice on the next couple pages, there are some graphs for you to look at and identify. You're going to decide which of those graphs matches the text describing the motion underneath it. I'm going to expect you to fill those in and send them to me. If you have any questions, you know where to look. Just reach out to myself, Professor Ashcraft. Rewatch the video.
Can I make a suggestion?
Oh, please.
I use my student ID here. I know it's upside down, but this is a wonderful thing to do tangent lines instead of a ruler for those little things. So use the tangent lines on the position versus time graph to figure out the velocities. Use the tangent lines on the velocity versus time graphs to figure out the accelerations, and that'll help you quite a bit. Have a good day.